I'm Lu.
I'm jamming.
Chaichi.
Today we will present about our ALU, and so I will go first. So this is our first, our full adder circuit. For this circuit, this shows the full adder get level schematic. This full adder adds two 1-bit arithmetic inputs A and B along with a 1-bit carry in CI, thus generating 1-bit output sum of A plus B plus CI and carry output CI1. This is our waveform. For example, if A equal to 0, B is 1, and carry is 1, 0, 1, 1, 0 plus 1 is 1, 0. So the sum is 0 and the carry is 1. So this is a 4-bit adder and subtractor. So for this 4-bit adder and subtractor, this circuit consists of 4 full adder, which I create the symbol for each full adder. And since operation of 4-bit numbers is performed, A and B will represent the 4-bit input values where the MSB to LSB indexing is indexed from 3 to 0, while the ALU option to add or subtract the number is connected to the XOR gate. When using quarters to design these circuits, the bus 2 is used to make connection that contain 4-bit information. Else, else if we use only single lines, the schematic diagram would be very messy and unnecessarily complicated. So for the waveform, I will show how to run for the waveform. So to perform the waveform, we first set this project as the top level entity, and then we analyze it. If completed, then we open for a new file, and then we open for the example. We simulation it. Okay, so for example, for the ALU operation is low, the ALU will perform addition, which 1 plus 2, 3 plus 4, and 5 plus 6. For the ALU operation is high, the ALU will perform subtraction with 15 minus 8, 13 minus 10, and 11 minus 1.
Next, I will be talk about the multiplexer. So the main function of the multiplexer is to combine and transmit signal over a single share medium to optimize the efficiency and decrease the total of the cost. And then this is the get level schematic of the 4-to-1 multiplexer. So the diagram shows that there will be 4 inputs, which I3 represent the MSB and I0 represent the LSB. So the 2 of the selected input of each 3 inputs and get will act as an enable. So for example, when the S1 and S0 is both 0 and then inverted, thus the I0 and get result in a high output, which is 1. And then the function of this logic circuit is tested and compiling using the waveform stimulation. So based on the waveform, it is confirmed that the multiplexer will select the input correctly and the output are copied according to the selected input. Next, this is the schematic for the 4-bit 4-to-1 mux. So the 4-bit 4-to-1 mux is used in the ALU to select the 4-bit A and B input and then route this input to the 4-bit adder and subtractor. And then the 4-bit input is sorted out and arranged using the bus line in twos in quarters as like the 4-bit adder subtractor so that it will look not messy. And then the mux is then compiled and stimulated in a vector waveform. So this is the waveform of the 4-bit 4-to-1 mux that we have stimulated. And based on the waveform, the mux is confirmed to function as expected, which is the output will follow the selected input. So for example, the I2 with the 1100 4-bit value is selected when the section input is 10. So the output is also following the input, which is 1100.
Okay, so I'm going to talk about the flip-flops and the register. In our ALU, our flip-flops are using a D flip-flop, which is a short form DFF. The D flip-flop and the register work together to store and process digital data. So in order to implement a 4-bit register, we have to implement the total of 4 number of the flip-flops, D flip-flop, in order to get our 4-bit register. So as we see in the quarters, you can see that there is the 4 D flip-flop arranged in parallel and then connected to a send D input to each D flip-flop. And also they are controlled by the common clock and reset. So this is the waveform from the quarters. When the clock and the reset is high, the Q will be followed the D input from the external input. So when the clock is high but the reset is low, the reset will return to be the 1. So the total block will be shut down. Then our QR will not follow the D input and become a 0, 0, 0, 0. So after combining those all blocks together, we get the arithmetic logic unit, which our ALU, which is the 4-bit adder and subtractor, 4-bit multiplexer, and 4-bit resistor. In this ALU, we are able to perform the arithmetic, which is the adding and the subtracting. Later on, we can also store the data after processed by the arithmetic circuit. So when the reset signal is excited to a high, the ALU becomes capable of capturing results from both the full adder and subtractor modules. Later on, the output corresponds to the sum of difference between the A and B inputs, with A0 to A3 and then the B0 to B3. And then it's determined by also the 4-to-1 multiplexer. So this is the waveform for the ALU design in our circuit. Okay, from the first one, we can see that when the reset is high, then it returns to become 0 since it's bubble. Then in the ALU, it will all perform the arithmetic, which are adding and the subtracting. And then after all, it becomes stored at the final output, which is a 0. And then we have a 5, 1, 1, and 0, and 3, and a 5 at the bottom over there. So this is our design of the ALU.